Thanks for the invitation. I'm very happy to speak here at the New Directions seminar. I hope you can see my screen. So the notes for this talk are available. You can either click on the link in the chat, or you can use this address bit.ly Keller's talk, all in small letters and in one word. And let me first point out that this is based on joint work with a student, PhD student Junyang Liu. Let me show you a picture. You have a picture of Junyang Liu. And my aim in this talk is to present an application of Vandenberg's superpotential theorem from 2015 to Amiot's conjecture on the structure of triangulated categories, which are two Calabi-Yau and have a cluster tilting object. The aim is to present an application of Michel Vandenberg's so-called superpotential theorem to Claire Amiot's conjecture. Yesterday, the theorem was published in 2015 to Claire Amiot's conjecture from 2010 on the structure of two Calabi-Yau triangulated categories with a cluster tilting object. Okay, yes, it's, if you like, the conjecture is a conjecture in the spirit of a Morita theorem. We know that if we have an abelian category with a small projective generator and suitably co-complete, then it is the module category of the endomorphism algebra of the generator. And the conjecture is in this spirit. We want to reconstruct the category from the endomorphism algebra of the cluster tilting object. And the plan is as follows. I will start by presenting a class of examples where Amiot's conjecture is known to be true, namely stable module categories over pre-projective algebras of Dynkin type. I will present this class as a motivation for the conjecture from pre-projective algebras to Amiot's conjecture. Then, in the second section, I would like to remind you of Vandenberg's superpotential theorem. And in the third part, I would like to apply this theorem to prove a slightly modified version of Amiot's conjecture. Let's just call this the application. Okay, so let's start with this very nice class of examples coming from pre-projective algebras. Okay, let's start with a Dynkin diagram, delta and A, D, E, Dynkin diagram. And then we choose an orientation, Q, a quiver, an orientation of delta. And then we work over the complex numbers for simplicity. And we consider pi Q the pre-projective algebra of Q. And we will, I will look at this in the example where Q is just a 3 with linear orientation. So pi Q is the pre-projective algebra of Q. So in this example, it is presented by the quiver where we double the arrows. We add an arrow in the opposite direction for each given arrow, and we impose relations. So these relations, we can either write them in compact form as the sum over the commutators of the old with the new arrows over all sum over all arrows of Q, or equivalently, yes. So if we multiply this row by the idempotents associated with the vertices on the left and on the right, then in this example we get minus beta star beta equals 0, beta star minus alpha star alpha equals 0, and alpha star equals 0. Yes, for each vertex we get a commutativity relation. Yes, here this composition equals this composition, and then here this composition equals this composition, which is 0, and here this composition equals this composition, which is also 0. Okay, and well, these are nice finite dimensional algebras because Q is a Dynkin quiver. Okay, since Q is Dynkin, pi of Q is finite dimensional. Yes, it is finite dimensional if and only if Q is Dynkin. When Q is connected, is finite dimensional, and moreover it is self-injective. It is injective as a module over itself. And so if we look at the category of finite dimensional right pi of Q modules, then this category becomes a Frobenius category. Yes, it's an exact category in the sense of Quillen. Here it is even abelian, and it has enough projectives and enough injectives, and the two classes coincide. And in that case, we know from Huppel's theorem that the associated stable category becomes triangulated. This is the quotient of the module category by the ideal of morphisms vectoring through projectives. this becomes triangulated by Appel's theorem from 1806. And well, this is one of the categories where we know that Amiot's conjecture is true. And it is a category where the remarkable properties are satisfied, which we need. We need the category to be through Calabi-Yau and to have a cluster tilting object. So let me state these facts well as a sequence of facts. So first of all, this stable category is through Calabi-Yau. This is a theorem due to Bergh from the year 2000. Now, what does it mean? Well, it means that if we look at X, well, there are several ways of phrasing it, but one way is to say, if we look at X between L and M and take its dual, then this is bifunctorially isomorphic to X between M and L in the other direction. Yes, this is a cell duality formula in dimension 2. And yes, so this is a very nice property. Then the second remark is, well, of course, if possible, one would like to classify the objects here, but that is almost always impossible. Yes, the preprojective algebra, even if Q is a Dynkin quiver, the preprojective algebra is wild in almost all cases. So it is representation finite or tame, if and only if the Dynkin diagram delta is among A1 up to A4 or D4 or A5. So it is almost always wild, and in particular representation infinite, but it has another very nice property, namely it is always two representation finite in the sense of Yama. So for an arbitrary Dynkin diagram, pi of Q is what is called two representation finite.
Bernhard, why you
Yes.
put A1, A4, and then A5 apart?
Well, I ordered them according to the number of vertices.
Ah, okay.
Yes, yes. And yes, for A5, it's going to be tame. Yes, and for the others, it's representation finite, if I remember correctly. Yes. Okay. Yes, so it is two representation finite in the sense of Yama's 2007 paper. And what does this mean? It means that the module category contains a so-called two-cluster tilting object, which is even canonical, but this is not so important here. Two-cluster tilting object T canonical. And well, here I've written it for the model category, but equivalently it is, we can formulate it for the stable category is equivalently the model category. As we have a bijection between cluster tilting objects in these two categories. And let me recall the definition in the sense of, in this case of the stable model category. So this is from Lena's 2007 paper. So an object T in such a triangulated category is, well, I will usually omit the 2 in 2 cluster tilting, because I will only look at dimension 2 in this talk. If 2 conditions hold, so first of all, T has to be a rigid object, which means that it does not have self-extensions. Next one of T with itself vanishes. And secondly, it generates the triangulated category in a very strong sense. It's a 2-step generator. Which means that for each object M, there is a triangle of the shape T1, T0, M, T1, where the TIs belong to the closure under direct sums and direct summons of T. Okay, so we can construct each object just as a cone over a morphism between such objects in the additive closure of T. And let me give you an example where we maybe first a remark. Yes, let me give you a remark. So one can deduce from this that if we know the endomorphism algebra of T, well, if we know the endomorphism algebra of T, then we know this category, and therefore we know the category of morphisms, and therefore up to isomorphism we know the classes, the objects of T. Yes, one can deduce that the endomorphism algebra determines the set of isoclasses of the stable of the triangulated category. Yes, we can, just by knowing the endomorphism algebra, we can recover the isomorphism classes. And then in the next step, we would like to recover the category itself. But before that, let's look at one example. Let us take for Q a linearly oriented A4 quiver. Okay, and then I will not give you the cluster tilting object, but just its endomorphism algebra. It is given by the following quiver with relations. We have a 3-cycle A, B, C, and and we have radical square 0. Okay, so the algebra here is very simple, and well, this algebra is of a very special type. It is a so-called Jacobian algebra. This means that this endomorphism algebra is a Jacobian algebra. So it is of the form J R W, the Jacobian algebra of a quiver with potential which looks as follows. We have the cyclic quiver A, B, E, and the potential is simply the D cycle. Okay, whenever we have a quiver with potential, we have the associated Jacobian algebra, which is the completed path algebra of the quiver with relations deduced from the potential, namely we form the so-called cyclic derivatives of the potential. For example, if we take the cyclic derivative with respect to C, we get A, B. If we take the cyclic derivative with respect to B, we get C, A. And if we take the cyclic derivative with respect to A, we get B, C. So you can see that we get exactly the three relations. They are all encoded in a very compact way in this single element, this three cycle in the path algebra. Okay, and well, as I said, this endomorphism algebra determines the isomorphism classes, but we are actually interested in reconstructing the category itself. And for this, we can pass from the endomorphism algebra, from this Jacobian algebra, to a refinement, a differential graded refinement, namely the so-called Ginzburg algebra. So the Jacobian algebra JRW has a differential graded refinement, namely the Ginzburg algebra.
Excuse me, can I ask one question?
Yes, please.
So in the original quiver, right, you have 4 idempotent elements, right? 1, 2, 3, 4. And in this, in the new one, right? In the morphism of this tilting, right? Tilting cluster, you have now three idempotent elements, 1, 2, 3.
Right.
Is it okay? I mean, I saw the
yes, it is okay. I mean, we look at the category which we consider. Yes, starting from this quiver, we consider the pre-projective algebra. Yes, where we introduce the additional arrows going in this direction and the pre-projective relations. And then we look at modules over this pre-projective algebra. And then we look at the stable category of modules over the pre-projective algebra. So in particular, in this category, all the projectives become 0.
I see.
And then inside this category, we look at one special object, this such a rigid two-step generator. And yes, so this is the object we're interested in. And this object, well, it turns out to be a sum of 3 indecomposable objects corresponding to these 3.
Okay. Okay.
Yes.
Okay. Thank you.
Yes.
Mhm.
Mhm. Yes. Okay. Yes. So we have the endomorphism algebra, and this endomorphism algebra allows us to recover the isomorphism classes of the category, but we want to recover the whole category. Yes, we are interested in the structure of triangulated categories. And we can do this if we look at this refinement of the Jacobian algebra given by the Ginzburg algebra. So let me describe the Ginzburg algebra in this example. What is the Ginzburg algebra for this quiver potential? It's the completed graded. Well, in this example, it's inessential whether we take the completion or not. But anyway, it's the completed graded path algebra of a quiver, a differential graded quiver R tilde. So this quiver is obtained from the given quiver R. This is the quiver R. In a slightly similar way as in the case of the preprojective algebra. So we have the 3 given arrows A, B, E. And then as for the preprojective algebra, we add new arrows. But now these new arrows are no longer in degree 0. They are in degree -1. A star, B star, C star. And these are of degree -1. And then we also add loops at the vertices of degree -2, T2, T3. So the degree of the TRs is -2. Okay, well, this is now a graded quiver. We can form the graded path algebra, and we can make it into a differential graded path algebra if we prescribe if we give ourselves the images of the generators under the differential. So for example, D of T1, yes, this will be essentially a commutator, namely this is C star minus B star B. Yes, this is somehow similar to the relation for the preprojective algebra, a commutator between old and new arrows. And similarly for the other loops, yes, T1 is in degree -2, and this is in degree -1. And then we also have to give ourselves the differential on the generators in degree -1. And here we use the potential. So the differential of this element of degree -1 by definition is the cyclic derivative with respect to A of the potential, and similarly for the others. And so we can see immediately that the homology in degree 0 of the Ginzburg algebra is isomorphic to the Jacobian algebra. So the Ginzburg algebra is concentrated in non-positive degrees, and its H0 gives us the Jacobian algebra, and it is in this sense that it's a refinement of the Jacobian algebra. And well, the Ginzburg algebra allows us to recover the category, the triangulated category. This is a theorem due to Amiot from 2009. Namely, we have a canonical triangle equivalence between the generalized cluster category associated with the quiver with potential and the given triangulated category, in this case, the stable module category of the pre-projective algebra, which takes the free module of rank 1 to the canonical cluster tilting object. And of course, I need to define what this cluster category is, but let me first show you a picture of Amiot. Okay, so now let me define the generalized cluster category. We are doubly mid term generalized of the quiver with potential, and this is defined as the perfect derived category of the Ginzburg algebra, where the quotient the perfectly valued derived category of the Ginzburg algebra. So yes, both are subcategories of the big derived category of this DG algebra. This is just the big subcategory generated by the free module of rank 1 inside the unbounded derived category. And this is the thick subcategory generated by the simple modules, the simple DG modules of this DG algebra associated with the vertices of the quiver. And this is, of course, also a subcategory of the big derived category of the Ginzburg algebra. Okay. Yes, so in this slightly surprising way, from the Ginzburg algebra, we can reconstruct the category, yes, with its triangulated structure as a value quotient. Okay, and now a little later, Claire Amiot conjectured that this should be a general phenomenon whenever we have a home finite 2 Calabi-Yau category with a cluster tilting object, we should have such an equivalence for a suitable quiver with potential. So let me write it down. Let's take C. A home finite dimensional morphism spaces. Carubian, so it has split idempotence. Triangulated category. With the following properties. So first of all, C is algebraic. So it is triangle equivalent to the stable category of a Frobenius category, or equivalently, it is the H0 category of some pre-triangulated DG category. Okay. Secondly, it is 2 Calabi-Yau. As a triangulated category. So we have this X duality. And thirdly, it contains a cluster tilting object. let's call it T. And then the conjecture claims that there should be a quiver with potential, or W, such that we have a triangle equivalence between the generalized cluster category associated with R and W and the given triangulated category, which takes the free module of rank 1. Yes, notice that the free module of rank 1 is, of course, in the perfect derived category and therefore in this Bergh quotient, and this should be sent to the given cluster tilting object. And so in particular, the endomorphism algebras are isomorphic. And well, this, it's not hard to see that this is the endomorphism algebra in the cluster category of the free module of rank 1. And this should be isomorphic to the endomorphism algebra. So as a consequence, we get that this endomorphism algebra is a Jacobian algebra. It's described by a quiver with relations which all come from the datum of the potential. Now, since the conjecture was stated, evidence has been accumulated for it. The first case where it's known to be true is the case where the endomorphism algebra of T is hereditary. As if it's given by its Morita equivalent to the path algebra of an acyclic quiver. In this case, the conjecture was proved in joint work with Idun Reiten already before it was stated in 2008. Then the second class historically is, of course, the one given by Amiot's theorem. So if we the category C is the stable module category of a pre-projective algebra of Dynkin type, and T is the canonical cluster tilting object, then it is okay by Amiot's theorem from 2009. Then it is also okay. Well, these categories also occur as categories of singularities or stable categories of Cohen-Macaulay modules. We take the stable category of G-graded Cohen-Macaulay modules over R, where R is a power series algebra in 3 indeterminates, and G a suitable cyclic group acting on it. And so for these cases, it is due on the one hand to Amiot, Iyama, and Reiten. In 2011, and also to van der Bergh together with his student Tannhofer de Velksy, published a bit later, but actually obtained simultaneously. And there are quite a few other classes where it is known. And now, well, what about the general case? Well, if we look at the conjecture, there is a certain incoherence in these conditions. Namely, in condition A, we assume that we are given an algebraic structure on C, but then in condition B, the two Calabi-Yau structure which we are given is given on C and not on the DG category A. So yes, so there's a certain loss of information. Yes, here we have this very fine information, and then here we only have relatively rough information on the H0 of A. So let's say this is a slight incoherence. In the conditions of the conjecture, namely the Calabi-Yau structure should be given on A instead of H0 of A. The Calabi-Yau structure should be given on the DG category A and not on its H0. Okay, yes, so there's an obvious modification of the conjecture where we give ourselves the Calabi-Yau structure on A itself and not on H0A. And now the main theorem obtained in joint work with Junyang Liu is that after this modification, the conjecture becomes true. After this modification, the conjecture holds. Okay, and the main tool in its proof is Vandenberg's superpotential theorem. So let me recall this theorem. It is a characterization of Ginsburg algebras. It is valid in any dimension greater or equal to 3, but I will only state it in dimension 3 because I only need it in dimension 3. So it's the following theorem. Published in 2015. Let's take a DG algebra, and it tells us under which conditions this DG algebra has to be a Ginsburg algebra. So A is smooth, connective, complete DG algebra which is endowed with a so-called left free Calabi-Yau structure. And then the conclusion is that it has to be quasi-isomorphic to a Ginsburg algebra. And A is quasi-isomorphic as a DG algebra to a Ginsburg algebra, or W for some quiver with potential R and W. And yes, so I should point out that the converse also holds. Every Ginsburg algebra satisfies these conditions. In particular, it carries a canonical left 3 Calabi-Yau structure. And this was shown by Michel Vandenberg before in 2011. And so now let me explain the terminology which I have used in the statement of the theorem. So first of all, what does it mean to be smooth for a DG algebra? Well, it means that if we consider the DG algebra as a bimodule over itself, then it should be perfect. AE, where AE is the enveloping DG algebra. Then what does it mean to be connective? Well, it simply means that homology is concentrated in non-positive degrees. In all strictly positive degrees, homology vanishes. Then complete, well, it means that the DG algebra is actually a DG algebra in the category of pseudo-compact vector spaces, which satisfies in addition a certain technical condition, which I will not make explicit, but this condition holds for completed connective DG path algebras. Okay, and finally, the left three Calabi-Yau structure. What is that? Well, it's a class beta in the third negative cyclic homology of A. So Hn denotes negative cyclic homology. So the three Calabi-Yau structure is the datum of this class, and it's not any class, it should be a non-degenerate class in the following sense. So, which is non-degenerate. And this means its image under the following map is an isomorphism. Yes, well, we can go from negative cyclic homology to Hochschild homology. And this Hochschild homology is canonically isomorphic to the space of morphisms in the derived category of bimodules from the bimodule dual of A to its third shift to the right. So HS is just the bimodule dual, derived bimodule dual. Okay. Yes, so these are the conditions. And now, yes, so its image under this is an isomorphism. Okay. And well, this is the theorem. And now we would like to apply this theorem to prove the conjecture. And this is the next step. So I see that I'm slightly behind schedule. So let me switch to the slides or to the notes. Just a moment. Yes. Yes. So let's try and apply this theorem to prove Amiot's modified conjecture. So now we take a home finite algebraic triangulated category. So it's the H0 of some pre-triangulated DG category C index DG, which has a cluster tilting object, and it has a right two Calabi-Yau structure. Yes, so there are two differences with Vandenberg's theorem. In Vandenberg's theorem, we have a left three Calabi-Yau structure, and here we are given a right two Calabi-Yau structure on this DG category. What is this? Well, it's a class also in the K dual of HC-2, where HC is now ordinary cyclic homology. it should also satisfy a non-degeneracy condition, which means again that its image becomes an isomorphism in the derived category of bimodules under a certain canonical isomorphism. And well, so we want to show that this category is actually a generalized cluster category. In other words, to say that it's a generalized cluster category means simply that we have an exact sequence of triangulated categories of this shape. As the Bergh quotient of the perfect derived category by the perfectly valued derived category should be equivalent to C. Okay, so we have, so the aim is to construct this sequence, the next aim. And well, let me maybe skip the details of the construction of this sequence. We use another characterization of the fact that C is algebraic, and using this characterization, we get a sequence of triangulated categories, an exact sequence of triangulated categories. Maybe some of you know this term. It is called the relative singularity category. So the relative singularity category is here the middle term, and one can show that it is the perfect derived category of some connective DG algebra gamma, and this is the perfect derived category of the Kossel dual of gamma. So this one shows this, and then one needs to show that this gamma, yes, so this gamma is the DG algebra A of Vandenberg's superpotential theorem, and we need to show that gamma satisfies the assumptions made on A, and the most important assumption is the existence of the left 3 Calabi-Yau structure. Yes, so we're given a right 2 Calabi-Yau structure on C, and we have to construct a left 3 Calabi-Yau structure on A. And for this, we use the long exact sequence in cyclic homology associated with this short exact sequence of triangulated categories. Yes, so more precisely associated with this, we have a triangle in the derived category of vector spaces, which links the cyclic homologies of these 3 objects. And then in particular, we have a connecting morphism, yes, which changes the degree. Yes. So for C, we're given something in degree 2, the class alpha. That's the class which is given through the Calabi-Yau structure on the DG category. And via the connecting morphism, we translate it into something in degree 3 for the DG algebra gamma. And then the subtle point is to check the non-degeneracy conditions. The non-degeneracy of alpha has to imply the non-degeneracy of beta. Okay, so this is a subtle point which one has to check, and which is one of Junyang's main contributions. And then once we know that beta is non-degenerate and that the other technical conditions hold, we can apply Vandenberg's superpotential theorem, conclude that gamma is indeed a Ginzburg algebra, and therefore the category C is a generalized cluster category. So thank you very much.
Thank you, Bernhard. Can we all unmute ourselves and give the speaker a round of applause?
Thank you.
Okay, do you have any questions for the speaker? There is a question in the chat, Bernhard, can you see it?
Mm-hmm. Yes, is anything, let me see. Is anything known about when the 2 Calabi-Yau structure on C automatically lifts to the some DG enhancement? Yeah, nothing is known to me. Yeah, yes, nothing is known to me. Yeah, it seems to be a very subtle question, and I have the impression that there must be examples of two Calabi-Yau structures on H0C, on H0C DG, which do not lift to the DG level. Yes, so, but it's probably quite difficult to construct them. Yes, it's the type of problem where, similar to the problem where you want to construct, say, a triangulated category without a model. Yeah, it's the same flavor of problem. So in the end, people have found such counterexamples, but it's not easy at all. And I would expect that there are such counterexamples here as well. Yes.
Okay.
And then let me see. There were a few questions before. Is it easy to see that pi of q is finite dimensional? Yes, because we know that the underlying quiver q representation, yes, if pi of q contains the path algebra of q, and so pi of q itself becomes a module over the path algebra, and we know that as a module over the path algebra, it is simply the sum of all the indecomposables. So since q is representation finite, this sum is a finite sum of finite dimensional modules, and so pi of q is finite dimensional.
May I ask one question?
Yes,
so you mentioned about this cluster tilting objects, right? But you didn't give explicitly the description, right?
No,
so,
I didn't make it explicit here. Yes,
but
right.
In general, is it? It's not a unique object, right? I mean, the description of such.
No. There are there's usually an enormous amount of such objects, except in the representation finite cases. Yes, in the representation finite cases, there's only a finite number of basic objects of this type. But in the other cases, there are infinitely many. Yes, and you can. Yes, I mean, there's the well-known operation of mutation, which allows you to construct infinitely many from a single one. Yes.
Right, and the endomorphism rings of such objects still will be Jacobian algebras, or
yes. Yes. For any object. Yes. So I mean, if you can. This is a consequence actually of the theorem.
Okay.
Yes.
Yeah.
It's at least yes.
And how about the other cases? For example, you are proving only for the ADE case, right? I mean, for the finite dimension case.
No.
Huh?
I mean, Amiot's theorem is for the ADE case. Yes. And but Amiot's conjecture is in complete generality. Yes.
I see. Okay. I see.
We share the screen. Yes. So Amiot's conjecture. Yeah. Here is the conjecture. Yes. So we take any Hom-finite Kohobian triangulated category. Yes, which satisfies these conditions. So this holds in particular for the stable module categories of pre-projective algebras of Dynkin type. But here it's stated in a completely general axiomatic setting, and there are many examples beyond this one. Yes, we have these examples, but then we have, for example, such examples which come from Cohen-Macaulay, graded Cohen-Macaulay modules, yes, which are of a quite different nature. Yes.
But do you cover all pre-projective algebras, all deformed pre-projective algebras?
Well, all pre-projective algebras of Dynkin quivers fit into this setting. Well, you can also look at deformed pre-projective algebras, but I mean, one essential condition is that our categories are Hom-finite. Yes. So if you take a pre-projective algebra, which is
Okay.
Yes.
Okay.
Of course. Of course, the other pre-projective algebras are also interesting, but they don't yield examples of such categories.
Yes. So what I mean is, for example, for the affine Dynkin clear case, right? You end up with those pre-projective algebras will be equivalent to the non-commutative Kleinian singularities, right? Which in many cases are actual Calabi-Yau algebras. So
Right,
but
right,
it's,
right.
yeah, it's not covered in this.
Yes,
Okay.
yes. If you like, I mean, the type of category which I'm considering, yes, this type of category is somehow similar to categories of finite dimensional modules
Right.
over Calabi-Yau algebras. Yes,
Right. Okay.
yes. So
Thank you.
it's yeah, it's on the causal dual side. Yeah.
Right. I see. Okay, thank you.
Thank you, Fakhr. Any other questions? Okay, if there are no more questions, let's thank Bernhard again.
Thank you once more for the invitation.
Yeah, no problem. Okay, I'll stop recording now.